Hello everyone, good morning to all of you. Myself, Dr. Mahadev Unde, Professor in Electrical Engineering, Jheel College of Engineering and Research, Pune. In a previous video lecture, we have learned the construction, principle of operation of three-phase synchronous motor, how it is not self-starting, how to make it self-starting, what are the various methods, etc. Now, in this video lecture, we are going to learn significance of load angle delta, the various cases, motor at no load and supplying no losses, motor on no load but supplying the losses, motor on load, then its equivalent circuit diagram, its phasor diagram, the current drawn, their equations, power flow diagram, and its power equation. Okay, now let us start. Here it is, the stator of the, already I have stated, the stator construction of synchronous motor, three-phase induction motor and synchronous generator is same. It has no physical appearance of the stator poles, but it is wound for a definite number of poles as per the requirement of the speed for the customers. Here I have shown the poles projecting away, physical appearance, but it is only for better understanding. Otherwise, there is no physical appearance of the stator poles. Rotor poles are visible, they are projecting away in case of salient pole machine. So in this case, this one is a rotor, then the rotor pole. For simplicity, we have considered only one stator pole and one rotor pole. Then this one is stator north pole and rotor south pole. South pole is considered. And when three-phase supply is fed to the stator winding, that is armature winding, it produces the rotating magnetic field. Say it is rotating in a clockwise direction. Then when the motor is on no load and supplying no losses, the stator polar axis and rotor polar axis coincides with each other, and there is no angle between stator polar axis and rotor polar axis. They are magnetically locked, and motor is supplying no load, so it does not draw any current. That means supply voltage equal to induced EMF in a magnitude and opposite in direction, and therefore the current flowing is zero. Now this is the second case. In this case, the explanation is similar to figure 1, except that this is at no load and supplying the losses. That means it is drawing some armature current. Here, if you observe carefully, this is the stator polar axis and this one is the rotor polar axis. So the angle between stator polar axis and rotor polar axis is delta. And there will be angle between delta between the VPH and EPH, that is induced EMF. This angle delta is known as load angle or a torque angle or a power angle. If you load the machine further, the rotor retards back and angle between stator polar axis and rotor polar axis increases, that is delta increases. Means as the load increases, angle delta increases. In this way, go on increasing the load on the machine, a stage will come, this angle delta becomes 90 degree electrical and there will be no magnetic locking between stator pole and rotor poles. Though here it is angle delta, but magnetic locking is still there and motor runs at a synchronous speed. However, as long as this delta is less than 90 degree, motor runs like a squirrel, like a synchronous motor at a synchronous speed. However, by loading the machine and when the angle delta becomes 90 degree, there is no magnetic locking between, or magnetic locking between stator pole and rotor pole break and motor fall out of synchronism. Okay, so this delta is once again known as load angle or a torque angle or a power angle. Its reverse happens, say the load on the motor is removed. So rotor will accelerate in a clockwise direction, and there will be angle between stator polar axis and rotor polar axis. Okay, and the details of this swinging of the rotor around about its axis because of sudden increase in load or sudden removing of the load is known as swinging, and we will study it later on. Okay, so here it is the cases. With losses, the rotor falls back and angle delta generated between stator polar axis and rotor polar axis. Current flows. If the load increases, delta also increases, and delta is known as load angle, delta angle, or the power angle. Now this is the equivalent circuit of the synchronous motor. See the armature side, the armature winding parameters. Obviously it is drawn on per phase basis. So armature winding parameters are the RA, armature winding resistance, and synchronous reactance Xs. They are connected in series. So their combination is Zs, and it is drawing the armature current IA. Phi is the supply voltage, and EB is the EMF generated in the synchronous motor. It acts in opposite direction to that of the supply voltage, and hence it is known as back EMF. The magnitude of this induced EMF EB is same as that of the generated EMF, that is 4.44 kc kd phi f tph. Okay, and this is the rotor circuit, which is generally excited by the DC source. This rheostat is used to control the field current or to vary the field current as per the requirement, or to vary the excitation system. This one is the phasor diagram, and in this case phi equal to the supply voltage phi equal to, see this EB acts in opposite direction, therefore phi equal to EB plus IA Zs, EB plus IA Zs. So this is VPH. Then IA drawn by lagging the voltage by an angle phi. This one is EB making an angle delta. This EB plus IA Zs will give you a phi. This is the phasor diagram with RA equal to 0. This RA is provided here. We will draw it later on with RA equal to 0. And therefore, IA equal to phi minus EB upon Zs, where the numerator, see numerator, there is no arithmetic difference, but it is a phasor difference, and this difference is nothing but ER upon Zs, and this ER can be obtained by multiplying ER equal to IA into Zs. Okay. Now see this voltage E equal to, supply voltage V equal to EB plus IA Zs, means this phi, supply voltage is always greater than the generated EMF, and this generated EMF acts in opposite direction to that of the supply voltage, and hence it is known as back EMF. So the IA equal to phi minus EB upon Zs, and that is nothing but ER upon Zs. The angle theta is nothing but tan inverse Xs upon Ra. Theta is the angle generated by ER and IA, and it is fixed. It is governed by the winding parameters Ra and L. And when armature resistance is negligible, theta is 90 degree. Otherwise, theta is always less than 90 degree. Now, in a previous case, see, here it is, the significance of the load angle. The motor is on no load and not supplying any losses. The phasor diagram is like this. The supply voltage V and the induced EMF, they are equal in magnitude but opposite in sign, and therefore this resultant ER is 0, and therefore it does not draw any current. So ER is 0 and armature current is 0. The waveform is shown, the blue color supply voltage V, and the generated EMF that acts in opposite direction to that of the supply voltage is shown by the magenta color, and that is exactly opposite to that of the supply voltage. This is the phasor diagram for the no load but supplying the losses. Phi pH is drawn as a reference. Then draw the current lagging the voltage by an angle phi. Then draw the EB by making an angle delta, reference to the phi. Join this parallelogram. Draw the line parallel to the phi pH, this one. Draw the line parallel to the EB. This is the resultant ER, and thus IA equal to ER upon Zs. This angle is delta. If the load on the motor is increases, this angle delta also increases, resultant ER also increases, because ER equal to IA Zs. ER equal to, see, ER equal to IA into Zs. So here load on the motor is increased, so ER increases, delta also increases, And the detailed diagram has been shown on the next page. Now pay attention here. Okay. If the rating of the synchronous motor is given in kVA, how to find the full load armature current? kVA into 10 raised to 3 divided by root 3 PL. If the kilowatt rating is given and power factor is known to us, the armature current is kW into 10 raised to 3 divided by root 3 PLIL cos phi. Now see, this is the phasor diagram. OA is the per phase voltage. Then IA is drawn lagging the voltage by an angle phi. Then draw the EB making an angle delta. Join this parallelogram, that is EB, and this VPH is nothing but this one. The triangle which is shown by the dark line is important as far as the problem solving is concerned. Now see, look at this. Draw the VPH in opposite direction shown by the dotted line. Similarly, draw the EB in a backward direction here. So what is the angle between EB and VPH? Delta. So angle between EB and VPH is delta. What is the angle between VPH and IA? IA is drawn opposite direction by the magenta color. So the angle between VPH and IA is phi, which is shown here. So what is the angle between EB and IA? EB and IA is shown by the green color, that is delta minus this phi. Delta minus phi. This may be phi minus delta, no matter. And therefore, the mechanical power developed in the armature, PM equal to EB, this EB into IA into cosine of angle between them, that is cos of delta minus phi. Okay. Now here it is the power flow diagram. Power per phase P in equal to phi IA cos phi. This is per phase power. Now out of this, see, here it is the stator CU losses and given by IA square RE, and rest of the power is mechanical power developed in the armature PM equal to EB into IA into cosine of delta minus phi. This is PM, mechanical power developed in the armature. Okay. Out of this PM, here are the rotational losses. That is iron, friction, and excitation losses. And rest of the power is nothing but P out, output power at shaft. Okay. So in this way, this is shown per phase power, or in other words, we can write PM is nothing but PM equal to P in minus stator CU losses. Okay. So in this way, we can show the power stages also. The power input minus stator CU losses. The remainder is mechanical power developed in the armature. If you subtract the rotational losses, that is iron, friction and excitation losses, remainder is the power output at the shaft. Now pay attention here. Power developed by the synchronous motor. Here it is. See, this is V. IA is drawn by lagging the voltage by an angle phi. draw the EB making an angle delta, then IA axis perpendicular to the IA, then in fact this arrow should be in this direction, and this angle is phi. Therefore AB, what will be the AB? AB equal to IA axis cos phi, and this dotted line is nothing but, say, A dash B dash, say this is A dash B dash, this A dash B dash equal to EB sine delta, and this is nothing but AB equal to IA axis cos phi. Okay, so from this, if you multiplying both sides by phi, multiplying both sides by phi, therefore phi EB sine delta equal to phi IA axis cos phi. So phi IA cos phi equal to phi EB sine delta divided by axis. This is nothing but P in equal to phi into EB upon axis into sine delta. So this is the power input. This is the expression for the power, or power generated by the synchronous motor. Okay, we'll stop here.